Welcome to this module. In the last module we have seen the criteria required for oscillations, right, and that in summary we have understood the Barkhausen criteria, right. Now in this module let us see how we can classify the oscillators, how we can classify these oscillators. So if you come back on the screen, what we can see is that the oscillators can be classified based on the nature of output of the waveform, the parameters used, the range of frequency, etc. Right. Nature of output waveform, parameters used, range of frequencies, etc. So, some of the classifications are based on output waveform, based on circuit components, based on operating frequency, based on whether feedback is provided or not. Right, you can see very easily how the oscillators are classified. So, based on output waveform, what does that mean? That the classified as sinusoidal and non-sinusoidal oscillators, right. So, either it will give us the sine wave at the output, or it will not give a sine wave. That means it can give a square wave, it can give a triangular wave, it can give any other waves which are not sine waves. So, either sinusoidal or non-sinusoidal, alright, sinusoidal or non-sinusoidal. Sinus oscillators produce purely sinusoidal waveforms, right, at the output. Non-sinusoidal produce waveforms like square, triangular wave, etc. Easy, very easy, right. Then based on circuit components, oscillators using resistors, capacitors are called RC oscillators, right. Resistors are, capacitors is RC oscillators. Those which requires inductors, right, and capacitors are called LC oscillators. Inductor L, capacitor C, LC oscillator. In some oscillators crystals are used, they are called the crystal oscillators. Okay. In some oscillators crystals are used and these oscillators are called crystal oscillators. So, very easy to remember based on circuit components as well. Now, let us see based on operating frequency how we can classify the oscillators. Okay. So, based on the operating frequency, the oscillators are classified as low frequency oscillator, audio frequency oscillator, LF, AF, high frequency oscillators or RF oscillators. The RC oscillators are used at low frequency and the LC oscillators are used at high frequency oscillators. So, based on frequency, if it is a low frequency oscillator, generally it will be RC oscillators. If it is a high frequency oscillators, it would be LC oscillators. So, based on the component we have seen, based on the output waveform we have seen, based on the frequency we have seen. Now, let us see based on whether feedback is used or not. So, if I see based on the feedback, the oscillators which use the positive feedback are called feedback type oscillators, and those which does not use any or do not use any type of feedback are called non-feedback type oscillators. The non-feedback type oscillators use the negative resistance region of the characteristics to generate the oscillation. The UJT relaxation oscillator type oscillator is example of such type oscillator, which is the non-feedback type oscillator. Alright. So, these are the types of or classification of the oscillators. Now, let us see first oscillator, that is our RC phase shift oscillator, RC phase shift oscillators. What are RC phase shift oscillators? A RC phase shift oscillator consists of an amplifier and feedback network made up of resistors and capacitances. The basic RC circuit is shown here, right. Now, let us see okay, what is VO equal to, if you want to find VO. So, if I say my input signal is Vm sin omega t, the impedance of circuit would be R minus j omega c, correct, where Xc equals to 1 by 2 pi Fc. So, tan of phi minus Xc by R or minus 1 upon 2 pi Fc by R, right. Xc is what, 1 upon 2 pi Fc. So, tan phi equals to minus Xc by R or this value. So, I would be nothing but this value, correct. That means what we see that when we have equation like this, the positive phase angle indicates that the current, you see here it is positive, So, that means indicates that the current leads applied voltage, the current leads the applied voltage by angle phi. Okay. The positive phase angle indicates that the current leads the voltage by phase angle or by angle phi. Now, VO equals to IR, right, is easy. As output voltage VO is dropped across the resistance, it is in phase, it is phase with current, hence the output voltage leads the input voltage by angle phi. Okay. In general, phi is called the phase angle of the circuit and depends on R and C selected. So, what we understand from this everything, this whole slide is that in this particular phase, since the current is leading the applied voltage by an angle phi, what we find is that the when the C is very large as compared to R, the phase angle tends to be 90 degree. That means, with one R and C, if C is extremely high than R, C is extremely high than your R, then my phase shift would be 90 degree. Phase shift would be 90 degree at the output. Okay. But in practice, the values are selected such that 1 RC will provide us phase shift of 60 degree, but the values are provided such that 1 RC provides a phase shift of 60 degree. Okay. So, if I want 1 RC is 60 degree. So, if I have a amplifier, that is my inverting amplifier, right. If I apply a signal, then my output would be 180 degree out of phase. This is 0, this is 180 degree. That means my feedback should produce another 180 degree phase shift, so that my feedback signal will also be 0 degree, correct. This we have seen. Now, 1 RC we have seen in last slide, we will adjust the value such that it provides 60 degree phase shift. So, how many RC circuits are required to provide 180 degree? Very easy, right, 60 into 3, 180 degree. That means, we require 3R and 3C, we require 3R and 3C. This is what is shown in this slide. This is what is shown in this particular slide, right. Let us see what is shown. Let us see once again. If the amplifier used causes a phase shift of 180 degree, the feedback network should provide 180 degree to satisfy the Biot-Christian criteria, right, because Biot-Christian criteria is that the input phase should be, the output feedback provided back to the input of the oscillator should be 0 degree in phase or 360 degree in phase, right. Hence, in a phase shift oscillator, 3 R sections of RC circuits are connected in cascade, each introducing a phase shift of 60 degree, each introducing phase shift of 60 degree, thus introducing a total phase shift of 180 degree. This is what we have discussed, right. Thus, RC phase network consists of 3 RC sections as shown below, which is shown right over here. So, if I have a signal at the input, my output would be 180 degree out of phase, 180 degree out of phase. Or in another way, if I, because this circuit, this is a beta, there is feedback network, the circuit is nothing but my beta, right, this one is my beta. So, if I apply output voltage which is 180 degree phase shift or out of phase with input, then my feedback to the input will again be 0 degree, because 180 plus 180, this is 60 from here, 60 from here, 60 from here. So, 180 degree phase shift, it becomes 0 or 360 degree phase shift, right. The network is also called a ladder network. All the resistance values, all the capacitance values are same. So, for a particular frequency, each section of RC produces a phase shift of 60 degree, right guys, very easy. So, if I want to design a phase shift oscillator using an operational amplifier, if I want to design a phase shift oscillator using an operational amplifier, how will I design? The phase shift oscillator can also be realized using op amp, instead of transistorized amplifier, op amp provides a stabilized gain setting. The feedback circuit used is same, right. You can see here. If I use transistor based amplifier, then it also okay, but if what we are studying is op amp based amplifier. So, this is the op amp. Now, here the advantage is that I can change the amplification factor by changing the value of RF and RI. Another point is whatever the I introduce phase, my output at the op amp, that is here, I will have a 180-degree phase shift, because it is a inverting amplifier. So, this 180-degree phase shift is provided to my RC network. So, here at this point I will have phase shift of 0 or 360 degree, right. This is what is written. The op amp is used in inverting mode, providing 180 degree. The RC network provides 180 degree phase shift. This is shown in figure. The gain of the op amp is adjusted with the help of resistors RF and RI, such that the product of gain of op amp and the feedback network is slightly greater than 1 to get the required oscillations. That means what is said, that the same thing again and again we will say in a different fashion, that to start the oscillation, initially my A into beta is kept greater than 1. Once the oscillations are reached, my A beta should be equal to 1, right. So, this you can change by changing the value of RF and RI. This you can change by changing the value of RF and RI. This feedback here, it is connected here, okay. It is connected here through the from output to the input, from output of the beta, that is feedback network, to the input of the oscillator. Okay. So, the effective RC feedback network is shown in figure here, right. So, this is Vi, this is Vo equals to Vf. So, applying KVL to various loop, what we have? What we will have is I1 into R plus 1 by j omega c minus I2 R equals to Vi, right. So, if I solve this thing, if I solve this equation, what will I have? What will I have? This particular equation. If I keep on solving this, I will have this equation. Now, if I replace j omega by s and write the equation in the matrix form, then I can write in this particular format, right. Now, everybody should know the Cramer's rule. So, using Cramer's rule, I can understand what is I3. I can understand what is I3. So, to obtain the value of I3, we have to use Cramer's rule, and then we can get I3 equals to this particular value. Now, as we know that Vo equals to Vf is I3 into R. So, if I substitute the value, then we have beta equals to, and beta equals to Vo by Vi, I will have this value. So, replacing S by j omega, because we have considered S equals to j omega, right here. So, we are replaced by S equal to j omega, and dividing numerator and denominator by this particular value, we will have beta equals to this equation, right. Now, again what we have to understand, to have a phase shift of 180 degree, the imaginary part of the denominator must be 0. What is imaginary part? Imaginary part is, imaginary part in the above equation is this part, right. So, alpha into 6 minus alpha square equals to 0, alpha square equals to 6, alpha equals to root 6. What is alpha? Alpha is nothing but 1 by omega RC, right, because we have used alpha instead of 1 by omega RC. So, we have 1 by omega RC equals to root 6, or omega equals to 1 by RC under root 6, right. So, what is omega? Omega is, right, omega and f. So, f equals to 1 by 2 pi r or root 6, right. You see omega is 1 by RC, right. So, I can write f equals to 1 by 2 pi RC root 6, correct. So, that we have substitute. Now, this is the frequency at which the oscillator will oscillate. This is the frequency at which the RC phase shift oscillator will oscillate. Now, at this frequency, beta is nothing but 1 minus, what is alpha? Alpha is root 6. So, we have beta equals to minus 1 by 29. Beta equals to minus 1 by 29. You understand? See, from here applying KVL, what we get? We get this equation. Now, if we rewrite the equation from a matrix, we can get this equation. From here using Cramer's rule we can get I3. Once we get I3 we can get VO. From VO we can get beta. From beta we can get the value which is this. Now to have phase shift of 180 degree, the imaginary term should be 0. When we do that we can get value of alpha, and then we can also have formula for f. From formula of f and substituting the value of alpha in the equation, then what will I have? I will have beta equals to 1 by 1 minus 5 under root of 6 whole square equals to minus 1 by 29. But I know that my Byer-Gaussian criteria will be satisfied only when a beta equals to 1, right. So, if my beta mode of beta is 1 by 29, my a should be greater than equal to 29, right, because my beta is 1 by 29, right. So, how can be equal to 1? This value, this is nothing but my beta, right. So, how this mode can be equal to 1 when my a should be equal to, a would be 29. So, 29 gone equal to 1, right. So, that is why that is what is shown, that if my beta is 1 by 29, my gain a would be greater than 29, right. So, to have oscillations, the gain of op amp must be equal to or greater than 29, which can be adjusted by changing the feedback and the input resistances. Okay. So, what we have seen in this particular module is that for the RC phase shift oscillator, all right, what we have seen in this module, and this is the last slide of this particular module, we have seen that for the RC phase shift oscillator we can design an oscillator. If we have an inverting amplifier, we have to use 3R and 3C to obtain a phase shift of 180 degree, because 1R and 1C will give us 60 degree phase shift. Then we have seen that for the frequency for the phase shift oscillator using R and C, we have frequency formula 1 by 2 pi RC into 1 by 2 pi R under root of 6. Then we have also seen that to sustain the oscillations, our A into beta should be equal to greater than equal to 1. So, from the solving the equation, what we find is we found that beta equals to 1 by 29. So, if I have the formula A beta is greater than equal to 1, my gain should be equal to 29, right. Thus, we know that whenever you have a phase shift oscillator, your A or gain should be 29 and your beta should be 1 by 29. You see again the important point is beta is extremely small compared to your gain value, right. If gain is 29, beta is 1 by 29. And another one is the phase shift of 180 degree. Why 180 degree? Because we have used inverting amplifier, right, we have used inverting amplifier. So, RC phase shift 3 RC will give us 180 degree, inverting amplifier 180 degree, 180 plus 180 360 degree, that is provided back to the input, Byer-Gaussian criteria is satisfied. Second one is A beta equals to 1, satisfied. So, satisfying both the criteria, we can now understand how we can design an RC phase shift oscillator. We can understand how we can design an RC phase shift oscillator. We will also see few examples of the oscillator in the experimental part. So, you actually see that how we are designing and how we are getting the output at the oscillators when we do not provide any input. So, initially we will have A beta greater than 1 and then it becomes A beta equals to 1. Right. So, now in the next module what we will see? We will see another class of oscillator, that is called Wien bridge oscillator. All right. In the next module what we will see? Another class of oscillators that are called Wien bridge oscillator. So, what are Wien bridge oscillators? We will see in the next module. Till then you just see this RC phase shift oscillator and its functioning. Okay. So, till then you read this stuff and I will see you in the next class. Bye.